Hello. Are you there, students?
Yes, ma'am.
Yeah, so whether you went through the lectures, video lectures, whichever I have shared.
Yes, ma'am.
So which topics we have covered? Up to uniform continuity, I have taken live lectures. Let me share the screen. Can you see the screen?
Yes, ma'am. Yes, ma'am.
Yeah, so up to uniform continuity, we have taken live lectures, right?
Yes, ma'am.
After that, sequence of functions. Just a minute. Equivalent metric is still remaining to today. I will take that. Then pointwise and uniform convergence, sequence of functions. This I have shared. I will show you the notes. (29) then 30, sequence of functions. I have shared these notes also. So video lecture of Reddy sir explaining these topics I have already shared. Everyone gone through it and taken the notes? Okay, so this sequence of functions, in that we have discussed like convergence, pointwise convergence and uniform convergence. Is there any doubt in these topics? These are important topics if we consider to net set examination as well, or any competitive exam. If you consider convergence and pointwise convergence of sequence of functions is very important. Already Reddy sir's lectures were there explaining this topic, so I have shared this. So whether you have any doubt in this? This is the exercise for you. Discuss pointwise and convergence of. Can you see the screen? If you are not replying, then no need to take live lectures, right? I will just conclude syllabus is over. मराठीत बोलू का? What is your problem?
आवाज येत नाही मॅडम क्लिअर.
माझा आवाज
मैम
येत
आवाज
नाही.
ब्रेक होता है आवाज.
एक मिनिट. Now check. Am I audible now?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So what I am asking, so whether you have gone through the lectures or not. And if some topic, if you need to revise it again, I will revise it.
Ma'am, that topic, the space of bounded functions.
Space
Can
of
you revise?
functions. Sequence of functions मध्ये काही problem नाही का? Okay, one by one I will open and let me know which topics is okay for you. Okay, in this sequence of functions, uniform convergence, pointwise convergence, we have already discussed, and some of the examples. Okay. So whether anybody has doubt in this? Okay, so the space of bounded functions. Up to here, no problem.
No, ma'am.
Okay. So in this, where is the problem? You didn't understand the space of bounded functions?
Yes, ma'am.
Let me write it. Okay, so what is the space of bounded functions? We denote it by b of x, which is a this b of x is nothing but space of all bounded real valued functions defined on x. X is any set. Okay, so b of x denote the set of all functions f whose domain is x and codomain is r. So we are saying it is real valued functions defined on x. But how are that f? All f are bounded. Then such set we denote as b of x, and we call it as space of all bounded functions defined on x. And we define norm on that b of x by norm f infinity norm, which is nothing but supremum taken x over x mod of f of x. So in that we have let me, okay, I will share this in just a minute so that I can write it. Okay, can you see this?
Yes, ma'am.
Okay.
Yes, ma'am.
Now I am writing. Can you see the cursor? The
Yes, ma'am.
space of bounded functions. It is denoted by b of x. What is this set? Set of all f from x to r. And moreover, this f are nothing but f is bounded. So we denote this space of all bounded functions by b of x, and norm we are defining by infinity norm, that is nothing but supremum x belongs to x mod of f of x. Okay. Now if fn converges to f pointwise in b of x, then fn converges to f uniformly. Okay. So fn converges to f implies norm of fn minus f in infinity norm also tends to 0. So what is this norm? fn minus f infinity tends to 0 means, this means supremum taken over x or x mod of fn x minus f of x, and this tends to 0. So this implies fn converges to f. Okay. Okay, after that, one theorem is there. If fn is a Cauchy sequence in B of x, then fn converges uniformly to some f belongs to B of x. I'm not writing it again. If fn is a Cauchy sequence in B of x, then fn converges uniformly to some f belongs to B of x. Moreover, if supremum is finite and this norm of fn converges to norm of f as n tends to infinity. Okay, so I think you might have gone through the proof. Is there any problem in the proof? If fn is a Cauchy sequence in B of x, means what? My fn's are real valued bounded functions defined on x, which is nothing but Cauchy, which satisfies Cauchy sequence property. Then if it is Cauchy, then fn converges uniformly to some f belongs to f of x. Means it limit also belongs to B of x. That we want to show here. Is that okay here? Or shall I explain the proof?
Ma'am, can you explain?
Okay. So what is given here? Fn is a Cauchy in B of x. So what is mean by Cauchy sequence? For every epsilon greater than 0, what happens?
There is measurement.
So, n and m such that
Mod of
n minus, now here norm, because it is a norm linear space. Okay, not mod. So norm of fn minus fm tends to 0 as nm tends to infinity. Actually it is less than epsilon, but that instead of less than epsilon, we are using this definition. Norm of fn minus fn in infinity norm tends to 0 as nm tends to infinity. So fnx minus fmx is less than equal to, by definition of this, is supremum. If we take modulus, okay, let me write here. What are my fn's? Fn's are nothing but functions from x to r. So where this fnx belongs to? It belongs to r, right? X belongs to x. So fnx belongs to codomain r. So on r we are taking modulus. So therefore fnx minus fmx, and which is always less than or equal to its supremum, x belongs to x. Can I write like this? Right? But this is nothing but my norm, right? Which is nothing but norm of fn minus fm, and this tends to 0 as nm tends to infinity. Is that okay?
Yes, ma'am.
So now fn is a Cauchy sequence in Bx. This implies fnx is a Cauchy sequence in R, right? And we know that every Cauchy sequence in R converges, because R is complete. Already we have proved this, right? So since fnx converges to some real number, say f of x belongs to R. So this implies limit n tends to infinity, fnx is nothing but fx. But what is fx? Mod fx can be written as modulus of limit n tends to infinity mod of fnx. So which is less than equal to this one. And this I can write as less than equal to limit n tends to infinity norm of fn infinity norm. Now since fn is a Cauchy in bx, it is bounded also. Is it right? Cauchy sequence is bounded.
Yes, ma'am.
Yeah. So the what is mean by bounded? There exists some constant c such that norm of fn is less than equal to c for every n. Therefore, mod of fx is less than equal to c for every x, and hence f belongs to b of x. Means this f is also bounded function defined on x. Is that okay? Now we show that fn converges to f. Okay. Now we want to show mod of fnx minus fx. This tends to 0 as n tends to infinity. Now consider mod of fnx minus fx, which is nothing but if I can write this as limit n tends to infinity mod of fnx minus fmx. Limit m tends to infinity I can take outside, supremum fnx minus fmx I can write, and this is limit m tends to infinity norm of fn minus fn, and since this tends to 0 as n tends to infinity, fnx minus fx tends to 0 as n tends to infinity. Therefore, we can, by definition, we can say that fn converges to f uniformly to f. And it is bounded also. So norm of this infinity norm of fn is less than equal to c for all n. This implies supremum of this also less than infinity. So we get modulus of norm of fn infinity minus norm f infinity is less than equal to this, which tends to 0, and we can say that this norm fn infinity tends to norm f infinity. Is that okay?
Yes, ma'am.
So this is all about sequence of functions. What was the which was the next one? Let me go to continuity and uniform continuity. Okay, so whether you have any problem in this continuity and uniform continuity? Let me go to the okay, continuity and uniform continuity already I have shared. It is next one was Weierstrass theorem, Weierstrass approximation theorem. So whether you have gone through this theorem, please reply me early so that I can go further.
Yes, ma'am.
Okay, is there any doubt in this? In this we have
Repeat, madam.
before proving the theorem, we have to prove here lemma. So before means proving this Weierstrass approximation theorem, we will require one lemma. What is that lemma? There is a linear isometry from C of 0, 1 onto C of AB that maps polynomials to polynomial. Okay, so for that we have proved means existence of isometry function we have proved. And then we have defined Bernstein polynomials B and f of x. So is there any problem in this Bernstein polynomial? It is just calculative part. Can you hear me?
Yes, ma'am. Yes, ma'am.
These Bernstein polynomials, in that some properties of Bernstein polynomials we have to prove, and then we will prove this actual Weierstrass approximation theorem. What is that? This Weierstrass approximation theorem says that given any f belongs to C of AB and epsilon greater than 0, there exists a polynomial p such that norm of f minus p is less than epsilon. Means what? We can approximate f with some polynomial p. What is the meaning of this? Every function f belongs to C of AB can be approximated with the polynomial p. Okay. So hence there is a sequence of polynomials Pn such that Pn converges to f on AB. So this we have proved. I think that is the last. That theorem is the last one here. So using Bernstein polynomials, we have proved this theorem. So is there any problem in this? Already Reddy sir has been explained in the videos. Hello students. Can you hear me? At least one student has to reply.
Yes, ma'am.
Okay. And the next one was equicontinuity. In equicontinuity, we have first defined uniformly bounded functions, uniformly bounded set, a collection of real valued functions f, it is actually script f, defined on x is said to be uniformly bounded if f of x, x belongs to x such that this set is bounded in R. Means supremum or f belongs to f, supremum x belongs to x, mod of fx must be less than infinity, or we can say finite. And then we define equicontinuity. Okay, continuity, uniform continuity, and then equicontinuity family of functions. Equicontinuity is also known as uniformly, see this, uniformly continuous. Right? Means it is collection of uniformly continuous functions, which is also again continuous, uniformly continuous. See here, this theorem we have already proved. Any finite subset of C of x which is equicontinuous where x is compact So our domain is compact. If our domain is compact, so any finite subset is equicontinuous on compact domain. And if X is compact metric space, F is totally bounded subset of Cx, then script F is uniformly bounded and equicontinuous. Then this is the very important theorem again, Arzela-Ascoli theorem. Let X be a compact metric space and let script F be a subset of C of X. Then script F is compact if and only if script F is closed, uniformly bounded and equicontinuous. This have you gone through this theorem? X is a compact metric space. F is a script F is a subset of C of X. Then script F is compact if and only if F is closed, uniformly bounded and equicontinuous. So whenever we want to show some set script F is compact, we will prove it as a closed, uniformly bounded and equicontinuous. And vice versa also. Just we have to apply the definitions of totally bounded, I hope everybody might have gone through this video lecture also. And is that okay?
Yes, ma'am.
Yes, ma'am.
Okay. If you are not yet gone through it, video lecture, you please go through it and take out your notes. Okay, now which topic is remaining? Equivalent matrix is remaining, so only one topic is remaining now. Let me. It is from third unit actually. This was remaining. Shall we continue today or tomorrow we can have this lecture? Okay, we can take today itself. Okay, so what is equivalent metric? Everybody know metric, right?
Yes, ma'am.
Yeah, metric is nothing but a function which satisfies some conditions. Okay, so let D and rho be two metrics defined on M, and I be a function from metric space MD to metric space M rho. See, set is same. D, but metric defined on M is different. Okay, here M together with metric D and M together with another metric rho. So this metric space is different. This metric space is different, and now we are defining a function on it. So it is I. And I inverse is nothing but reverse. I inverse is nothing but its domain is M rho and codomain is MD. Is that okay? Now
Yes, ma'am.
consider the I and I inverse be identity maps. Then we say that D and rho are equivalent D and rho are equivalent, means two matrix are equivalent if and only if both I and I inverse are continuous. Okay, so when we say that two matrices are equivalent to each other, if if these identity maps defined from MD to M row and inverse identity map I and I inverse both are continuous, that is I is homeomorphism, then we say that it is that two matrices are equivalent to each other. Now I is continuous means what? If for given epsilon greater than 0 there exists delta greater than 0, by definition of continuity, rho of ix comma iy is less than epsilon whenever d of xy is less than delta. Similarly, what is mean by I inverse is continuous? D of xy is less than epsilon whenever rho of xy is less than delta. Okay. D and rho are called now uniformly equivalent if I and I inverse are uniformly continuous, and D and rho are called strongly equivalent if I and I inverse are Lipschitz map. See here different definitions. D and rho are called first just equivalent if I and I inverse are continuous. Okay, what is next one? It is strongly equivalent. When we say that it is strongly equivalent if I and I inverse are Lipschitz function. What is mean by Lipschitz functions? Lipschitz continuous. What is mean by Lipschitz map?
Rho of f of x.
There exists alpha lying between. What is that?
There is alpha such that rho of f of x comma f of y less than that k alpha of d of f of
K
x and
or
y.
can say there exists constant k such that distance rho of f of x comma f of y is less than k times
D of x square.
d of depends on metric, what metric is defined, d of xy. Okay, and what is uniformly equivalent? So if I and I inverse are uniformly continuous. Okay, shall I write here? Uniform, you can just have the look in change in definitions. Equivalent, uniformly equivalent and strongly equivalent. In equivalent, I and I inverse are continuous. For for uniformly equivalent, I and I inverse are uniformly continuous, and for strongly equivalent, I and I inverse are Lipschitz continuous. Okay, Lipschitz map. So by definition of continuity, uniform continuity and Lipschitz, we already know that which implies uniform continuity implies continuity.
Yes, ma'am.
So this implies uniform, equivalent implies equivalent, and Lipschitz map is uniformly continuous as well as it implies continuity. Therefore, strongly equivalent implies uniform, equivalent implies equivalent. Okay, but converse is not true. This example is already given. Okay. Like what is the converse is not true? If you take d of xy is equal to modulus of x minus y and rho of xy is equal to under root modulus of x minus y, m is equal to 0, 1. So what can I say here? What is mean by converse is not true? Means equivalent does not implies uniformly equivalent or strongly equivalent. Actually, it is by it follows from continuity does not implies continuity does not implies uniform continuity, right? Uniformly continuity, or it does not imply Lipschitz. Already in that section we have taken some examples which does not follow this. Okay. Therefore, strongly equivalent implies uniformly equivalent implies equivalent, but this is need not be true. Now suppose that MD is compact and rho is another metric on M. Then D and rho are equivalent if and only if D and rho are uniformly equivalent. Okay, what we want to show here, MD is given to be compact. D is metric defined on M. Rho is another metric defined on M. D and rho are equivalent if and only if D and rho are uniformly equivalent. Again, this follows by the definition. But equivalent and uniformly equivalent. Check this. Which follows obvious? Uniformly equivalent implies equivalent always.
Yes, ma'am.
But equivalent does not imply uniformly equivalent. But if provided my MD is compact, if MD is compact, then equivalent implies uniformly equivalent, because we already proved that a continuous function on compact domain is uniformly continuous. Is that right? A continuous function on compact domain is always uniformly continuous. Therefore, this equivalent implies uniformly equivalent there. Can you recall that definition? Let D and rho be equivalent. So by definition, I and I inverse are continuous. Now MD is compact. So I and I is continuous, means I is uniformly continuous. Also I inverse is continuous. And onto, therefore I inverse of M rho is nothing but MD. And it is also compact. Since I is continuous, M rho is nothing but I of I inverse of M rho, which is also compact. Therefore, I inverse is also uniformly continuous. And this implies D and rho are uniformly equivalent. Conversely, D and rho are uniformly equivalent. Therefore, D and rho are equivalent. This follows obviously. Is that okay?
Yes, ma'am.
Now, next theorem. Let V together with this norm and W with the norm, this V and W be two norm vector spaces, and T from V to W be a linear map. Then the following statements are equivalent. What is the statement? T is Lipschitz, T is uniformly continuous, T is continuous everywhere, and T is continuous at 0. T is there exists a constant C such that norm of Tx is less than or equal to C times norm of X for every X in V. Okay, so what is given here? T is a linear map from vector space to another vector space V to W. V together with this, actually they are non-linear spaces. Okay, and we want to prove these 5 statements are equivalent. So we will prove this. 1 implies 2, 2 implies 3, 3 implies 4. Okay. Let me go below. So what is first statement? T is Lipschitz. Since now 1 implies 2, 2 implies 3, and 3 implies 4, they are trivially true by definition of continuity, uniform continuity and continuity. Already we know this.
Yes.
Lipschitz implies uniform continuity. This implies continuity, right? So 1 implies 2, 2 implies 3, 3 implies, and continuity everywhere implies continuity at 0 also. Continuity at 0, right? So 1 implies 2, 2 implies 3, and 3 implies 4. They are trivially true, right? So no need to prove because it follows from the definition. Only we want to prove 4 implies 5 and then 5 implies 1. Okay. So it is sufficient to prove 4 implies 5 and 5 implies 1. So that we can say that all 5 statements are equivalent to each other. So come to the proof of 4 implies 5. What is 4? T is continuous at origin. And we want to show there exists a constant C such that norm of Tx is less than or equal to C times norm of X. Now see, since T is continuous at 0, for epsilon is equal to 1, there exists delta greater than 0 such that norm of Tx is less than 1. Is that right?
Yes,
By
ma'am.
continuity definition, for every epsilon there exists delta. So for epsilon is equal to 1 also there exists delta which satisfies this condition. Is that right? Norm of Tx minus T at 0 is less than epsilon, but epsilon is my 1. Is it right? And T of 0 is 0 because it is a linear map. So norm of Tx is less than 1. We are getting here. Is that okay?
Yes, ma'am.
So for epsilon is equal to 1, there exists delta greater than 0 such that norm of norm of Tx is less than 1 whenever mod of x minus 0 is less than delta. So norm of x whenever norm of x minus 0 is less than delta. This by definition of continuity. Here, so we are getting whenever norm of x is less than delta. Now let x is non-zero and define x dash is equal to delta x upon 2 times norm of x. Then I can write this norm of x dash is equal to norm of delta x divided by 2 norm of x, and which is nothing but delta upon 2 norm x into norm x, and which is nothing but delta by 2, and which is absolutely less than delta. Therefore norm of tx dash is strictly less than 1, and this, what is my x dash? X dash I have taken as delta x divided by 2 upon 2 delta x divided by 2 into norm of x, and which is less than 1. Therefore I can say delta upon 2 norm x into norm of tx is less than 1. And this implies norm of Tx is less than 2 by delta into norm x, and that 2 by delta if we take as C, then I can say that there exists constant C such that norm of Tx is less than or equal to C times norm of x, where the C is finite. Now I want to prove fifth implies 1. What is fifth? If there exists constant C satisfying norm of Tx is less than C times norm of x, then we want to prove T is Lipschitz. So suppose there exists such constant C. Okay. So this implies norm of Tx minus Ty is equal to norm of T of x minus y, which is less than or equal to C times norm of x minus y. right? This is for every x and y. So what this implies? T is Lipschitz by definition. Here you can see norm of T of x you can write, or just T of, okay, T of x minus T of y is less than equal to, we are getting C times norm of x minus y, and C is constant. Okay, therefore we can say that there exists constant C which satisfies this condition, therefore T is Lipschitz. Is that okay?
Yes, ma'am.
Now next theorem. Any two norms on a finite dimensional vector space are equivalent. Any two norms on a finite dimensional vector space are equivalent. If I remove this finite, then it is not true. Okay. Any two norms on a finite dimensional vector space are equivalent. It is not true for any vector space, but it is true only for finite dimensional vector spaces. Okay. So let V be a finite dimensional vector space of dimension n. What is meant by finite dimension? Number of elements in a basis is finite, right? So let x1, x2, xn be a basis for V. Then for any x in V, there exists alpha 1, alpha 2, alpha n belongs to R such that x can be written as linear combination of alpha I into xi, right?
Yes, ma'am.
But from linear algebra, you can recall every vector x can be written as linear combination of basis elements of basis. Now define a map f from V to Rn by fx is equal to alpha 1, alpha 2, alpha n. Now we define a norm on V as norm of x is equal to summation I is equal to 1 to n alpha I xi, which is nothing but summation I is equal to 1 to n mod of alpha I. Now this f is isometry. What is mean by isometry? A map is said to be isometry if it preserves distances, right? A map F is said to be isometry if it preserves distances. Therefore, norm of x is nothing but my summation I is equal to 1 to n mod of alpha I, and which is nothing but norm of f of x1, because mod of alpha I can write as norm of alpha 1 comma alpha 2 alpha n. Therefore f is an isometry because it preserves distances. Now consider another norm on V. So if I denote this triple norm, we can say another norm I want to define. So I am defining like this another norm notation. Be another norm on V. Then what is norm of this x? This is nothing but norm of summation I is equal to 1 to n alpha I xi. This I can write as summation less than or equal to summation I is equal to 1 to n modulus of alpha I triple norm of xi. But it will be always less than equal to maximum also. So this is less than equal to maximum of triple norm of x into summation I is equal to 1 to n mod of alpha I. But this maximum or this norm of xi is nothing I can denote as some c1, some constant, and so constant times summation I is equal to 1 to n mod of alpha I. But this mod of alpha I is nothing but norm of x again. So norm of x is less than equal to c1 times norm of x. Now let denote the set as such that x belongs to V, where norm of x is equal to 1. Now f is isometry as already proved, and f of s is compact in Rn. It implies S is compact in V. So this norm defined on V to R is continuous as norm of. Now just apply the definition of continuity. Okay, so triple norm of x minus triple norm of y is less than equal to norm of x minus y, triple norm. This notation you have to remember, okay, which is less than equal to C1 times norm of x minus y. So this implies this this triple norm is continuous on S. Now since S is compact, this attains its maximum, say C2, right? On compact metric space of continuous function attains its maximum and minimum. We already proved that theorem. Can you recall the theorem? Are you there, students?
Yes, ma'am.
Yes, ma'am.
Yes. So since S is compact, this norm is continuous. It attains its minimum value, say C2. There exists C2 greater than 0 and norm of x is greater than equal to C2 for every x in S. So for any x non-zero, x upon norm of x is also belongs to S. This gives me the norm of x upon norm of x is greater than equal to C2 for all non-zero x belongs to V. Okay, so we are getting this. Now from 1 and 2, I and I inverse are continuous. Therefore, this norm and this norm are equivalent. See, here we have denoted two different norms. Okay, this and this. These two norms are equivalent, and we are proving this I and I inverse are continuous. I from V with this norm to V with this triple norm. Okay, and inverse is where, from where to where? V with triple norm to V with double norm. Is that okay? So where will be I of x? This will belongs to if I want to take norm of Ix, if x belongs to V, just I will write norm x. If I want to write norm of I of x, what will be the norm? It will be triple norm. Is that right? Because it belongs to codomain. Are you getting this? V with this norm and V with this norm. It is different. Are you getting this difference? Space is same. Norm is different only. Hence, two norms are on a finite dimensional vector space are equivalent to each other. Now, corollary. Let V and W be normed vector spaces with V is finite dimensional, then every linear map T from V to W is continuous. So V and W be norm vector spaces and V is given to be finite dimensional. T from V to W is a linear map and V is given to be finite. Okay, then every linear map we want to prove it is continuous. We want to prove every linear map from finite dimensional vector space is continuous. Now since V is finite dimensional, there exists a basis, say x1, x2, xn be a basis of V. Then for any x in V, again we are defining the same thing. Linear combination x can be written as linear combination of xi's. Now let this triple norm be a norm on W. Then for any x in V, norm of Tx can be written as norm of T of x is written as linear combination of xi's. Okay. Now since T is linear, I can write this as summation alpha I T of xi. Is that right?
Yes, ma'am.
Now this summation alpha I mod of alpha I, if I from norm I am taking outside, so summation I is equal to 1 to n mod of alpha I into triple norm of T of xi. So C times summation I is equal to 1 to n mod of alpha I, where C is nothing but this maximum over this. So this implies norm of Tx is less than equal to C times norm of x. So this implies T is continuous. Okay, so every linear map from finite dimensional vector space is always continuous. Now next theorem, let D be a dense in M and N be complete. Then F from D to N be uniformly continuous just a minute. Do you have lecture now?
Yes, ma'am.
Okay. Just okay. So we will prove this remaining part. Only one theorem is remaining actually. Okay. Anyhow, tomorrow we will discuss this. Okay. This
Okay.
theorem we will discuss tomorrow.
Okay, ma'am. Okay, ma'am.
Okay. Okay, you can leave now. हा हॅलो सर बोला ना.